Bonjour, bienvenue pour la soutenance de thèse de Zhuzhi Fan. Donc, we will switch to English because the member of the jury we will speak in English and your defense will be in English. So, my name is Laurence NIGAY. I'm professor at the University of Grenoble, and I will serve as a president of the jury today. Zhuzhi was co-supervised by Céline COUTRIX, who is a researcher here at the Computer Science Laboratory, and with Benoît ROMAN, who is a CNRS research director in Paris. And I would like to introduce the members of the jury. So the two referees of your PhD are Anne ROUDAUT, who is a professor at the University of Bristol, Jan Borchers, a professor at the University of Aachen. Ad and Jan are participating by video conference, so they are there. The two examiners are Maud MARCHAL here, who is a professor at INSA, French National Engineering School in Rennes, and Kenny Zhu, an associate professor at City University of Hong Kong, and Kenny is participating by video conference. And so now, Zhuzhi, you will present your research, and we will have a discussion session with the members jury afterwards. So you have more or less 45 minutes to present your work.
Thank you for the introduction. Hello, I am Zhuzhi. I will happy to present my PhD thesis, Interaction through Programmable Software Materials. From the title, you might know my thesis focuses on two research aspects. One is a human-computer interaction, and the other is programmable software materials. Before we go forward with questions such as what are programmable software materials and how we can interact with them, let's see together a video of one commonly seen when magnificent animal in the world, an octopus. Nature is awesome. Watching this video of an octopus is purely soft and has no rigid part such as bones. Meanwhile, it has a remarkable shape-changing ability. It can rapidly change the shape to imitate its surroundings, pass through small tunnels, and swim and hunt. It would provide us totally new interaction experience if every device, like phones, computers, and tablets, could do the same. However, even with the latest devices, such as one of the newest foldable smartphone, it can only be manually folded or unfolded by users. With its limited configurations, it can already bring us new user interaction experiences. For example, we can fully fold the phone to improve its portability, partially fold the phone to use it as a handheld video recorder, partially fold it to take a selfie at a distance without using a phone holder. However, current devices have some limitations that need to be overcome. For example, they currently use rigid materials that are not stretchable, making them unsuitable for wear on the body. They are not actuated and can only be changed their shape manually by users. These limited applications, for example, the change of the shapes cannot be used for notifications. They have limited shapes configuration, which limit functions. To overcome these disadvantages with our current devices, one question that needs to be answered is how we can build novel devices with soft materials and actuate them to have more shape changes, to provide users with novel interaction experiences. That's what I searched for in this thesis. Certainly, emerging programmable software materials give us a high potential to realize it. Let's start with the question, what are programmable software materials? Firstly, they are made of soft materials, such as elastomers, hydrogels, and fabrics. They are deformable when external stress is applied, for example, when we straighten or press on them. Secondly, they can be programmed to change a design shape in response to various external stimuli. For example, an elastomer plate with air channels embedded inside can be inflated into a mask shape like a human face. A hydrogel film immersed in water can morph into a helical shape during the hydration process. A dielectric elastomer plate can morph into a sinusoidal shape when a high voltage is applied to it. When heated, a piece of fabric woven with heat shrinkable elastomer fibers can morph into a cone shape. Thanks to the remarkable shape-changing abilities of programmable software materials, emerging shape-changing UIs were developed with novel interaction experience to provide users with novel interaction experience from different aspects. For example, a watch can vary its beating speed according to users' current heartbeat for regulating their heart beating rhythm. When playing a game, a tablet case can morph from a flat shape to a handheld controller with a more ergonomical shape. On a rainy day, a phone case can curve to cover the screen to help users type on their phones. A phone can also change its shapes to notify users when receiving a call or a message. A glove with surfaces that contact with user fingers can change shapes to simulate different objects that the user touch in the virtual environment, such as the chord of the violin, as shown in the video. There exist emerging programmable software materials which indicate a high potential to construct shape-changing UIs with them. Meanwhile, there is a high demand for shape-changing UIs for various purposes. The research question of how to better integrate programmable software materials into shape-changing UI development is timely to be answered, and various challenges need to be addressed. Like the other research areas of shape-changing UIs, the existing grand challenges can be categorized into 4 groups. In this thesis, I focus on 3 of them. More specifically, to address the technological challenges, I conducted a technological exploration of programmable software materials to control different shape-changing UIs, and develop a novel technology to address the stretchability strength trade-off of current programmable software materials. As for user behavior challenges, compared with the traditional rigid UI, the adoption of programmable software materials in constructing shape-changing UIs introduced a new factor, that is softness, which might impact user interaction experience. To address this challenge, I conducted a psychophysical experiment to study the impact of material softness on user shape perception ability. As for the design challenge, based on our previous technological exploration on constructing shape-changing UIs using programmable software materials and the user study of the impact of softness on their shape perception ability, I designed a novel wearable device using programmable software materials to provide users with novel haptic feedback through their shape changes. Here is the plan of my thesis. Now, I have finished my introduction. Let's go together to the technology exploration part. I will start this part by presenting my exploration of using programmable software materials for constructing different shape-changing UIs. Most current shape-changing UIs use one type of programmable software materials to develop proof-of-concept prototypes for specific applications with limited types of shape changes. However, prototyping shape-changing UIs with the new materials still has a high barrier for HCI researchers, as there is a need for awareness and understanding the shape-changing technologies and their material characteristics. In this thesis, I started addressing these barriers by conducting technological explorations of programmable software materials to conduct different shape-changing interfaces that the HCI researchers needed. And I majorly focused on a new material called Bâtiment. They are elastomer plates with air channels embedded inside. Their shapes after inflation are decided by the shapes of air channels and the air pressure. We choose this type of material for its multiple advantages. Firstly, they're made of silicon elastomer, which ensures their softness and high durability. These characteristics are important for wearable applications. They're actuated through pneumatic inflation with off-the-shelf pumps without the need for heating or high voltages. And they can rapidly change the shapes when inner pressure changes, as shown in the video. With the air channels of different shapes, Bâtiment permits the creation of various shape changes from a simple hemispherical shapes to a more complex shape like a human face mask. To explore the use of Bâtiment in shape-changing UIs development, we need to decide which shape changes to realize are needed by HCI researchers. For this purpose, we reference to the Morpheus plots one refined shape changing and shape engine UI technology based on two previously most cited technologies. After a thorough technological exploration, I developed Softomorphics, a series of 6 different shape changing modules using programmable software materials. It's currently the only technology that permits the creation of so many shape engine features using programmable software materials. I will now present some of the shape changing modules that I developed. I also provide their shape measurement under different air pressures to facilitate other HCI researchers' design. Let's start with one lens changing module example. Here's the lens changing module that I developed. The top figure presents the shape of the air channels embedded inside. To ensure the module expands its length instead of bulking out as a usual barrel when pressurizing, I carefully fabricated it with equal top and bottom membrane thickness, that is 1.2 millimeters. The same thickness for the external wall. The same values were designed for air channel width and the distance between channels. Here's a video of the length changing module with different air pressures. We can see that its length increases more rapidly as the air pressure increases. This is consistent with our measurement of its length under different pressures. An proportional function can well fit an increase in length by air pressures. In total, with pressures increase from 0 psi to 6 psi, I measured a 30% length increase. I will now present the amplitude changing modules. I designed a series of modules with the same air channel width of 1.2 millimeters. While different distances between channels from 1.2 millimeters to 6 millimeters, which lead to different ratios between air channel width and the distance between channels. Here, I present the module with a ratio of 2 as an example. You can find the detailed presentation of all the amplitude changing modules in my thesis. Here is a video taken from the side view of presenting the amplitude change of this module. We can see that the amplitude increasing speed is not constant with pressure. Here is my measurement of its amplitude under different pressures. And we observed that when the pressure is less than 7 psi, its amplitude increases slowly. With the increase in pressure by 7 psi, I measured a 2.6 millimeter increased amplitude. When pressure is larger than 7 psi, its amplitude increases more quickly. Pressure increasing from 7 psi to 12 psi can lead to a 17.8 millimeter amplitude increase. Here is the amplitude measurement of different prototypes with air channels distance width ratio varying from 1 to 5. We can see that under the same pressure conditions, for example, 12 psi, the prototype increased less in amplitude with an increased ratio. We also observe that with an increased ratio, the prototype has the tendency to need a larger pressure to start the quick shape change. The threshold increases respectively from 5 psi to 8 psi. Future work should measure the exact threshold more precisely, particularly for modules with ratios between 2 and 4. I will now present the zero crossing module. The zero crossing module is composed of 4 inflated bending branches. All 4 branches have the same air channels width of 1.2 millimeters. While each branch has a different air channel distance from 1.2 millimeters to 2.4 millimeters. This leads to the 4 branches having different distance width ratio ranging from 1 to 4. We observe that the larger ratio will lead to the branch needing higher pressure to bend. Here are 2 synchronized videos presenting the different shapes of the zero crossing changing module. The top is taken from the side view, and the bottom is taken from the above view. We use green curves in this video to present branches bending after inflation and increasing the zero crossing value. The plot on the right presents the zero crossing values in different air pressures. It increases progressively from 0 to 4 when the pressure increases. This slide presents videos of some modules I developed addressing different shape changes. You can find in detail in my thesis their design and shape change measurement. In summary, I explored the new material biomorph and developed Softomorphics, a series of modules to realize various HCI-oriented shape changes. I also conducted respective shape measurements and the regression analysis. This can significantly facilitate other HCI researchers' development of their shape changing and UIs using these new materials. Now, let's move to the technological exploration for addressing the limit of current programmable surface materials. Through our technological exploration of biomorph, we have seen the high potential of using the elastomer-based new material to construct UIs with a remarkable shape-changing ability. However, its trade-off between the high stretchability and low strength will further limit its application in HCI. More specifically, softer materials like elastomers usually have high stretchability, which makes them easy to deform, thus having a high potential to create many shape changes. Meanwhile, it's easy to deform, which usually means low strength. The strength of UIs is important when we use them in HCI applications, particularly when we use them to provide users with haptic feedback. For example, the bladder in the red circles is rigid and strong enough to support the user's finger when pressing on it. The bladders in blue circle are soft and cannot support the finger. To address this trade-off, I explored technologies to enhance the strength of UIs built with soft materials like elastomers. Then they're combined with shape-changing technology to control both UI's shape and strength. Various technologies have been developed to enhance UI's strength. I will introduce them in detail in my thesis. Here, I focus on one frequently used strength controlling technology in HCI research, jamming. Here is a demonstration of jamming. I show in this video an elastomer bladder filled with glass beads has low strength and it's easy to change its shape. When the air inside is extracted, particles inside are jammed together and lead to the whole bladder's increased strength, and it becomes more difficult to change its shape. Jamming technologies have many advantages to change the strength of UIs, such as rapid and continuous strength change. However, how can we combine jamming technology with other shape-changing technologies to control both UI's shape and the strength? Current solutions usually overlay direct jamming layers over another shape-changing interfaces. For example, a designer can add a jamming layer over an elastomer membrane-covered air chambers to create a surface with changing softness and curvature. I show in this video. Before the air of the jamming layer is vacuumed out, the jamming layer can be pushed to be curved when preserving the air chamber underneath it. In this state, the surface that the user touch is soft. And the air inside the jamming layer can be vacuumed out to stiffen the surface from soft to a much more rigid. However, adding an extra layer of jamming will lead to an extra thickness. For example, nearly an extra 8 mm here. Increased thickness might limit the applications, particularly for wearable devices. Moreover, they need multiple actuators, for example, at least one actuator needed for controlling the pressure inside the air chambers, and another one for controlling the pressure inside the jamming layers. The need for multiple actuators might lead to use as in reduced portability. For this reason, we developed a new technology, jamming origami endocyclone, with the team from Benoît's lab. This enables the control of both UI's shape and strength using only one actuator and does not add extra thickness. Here is a prototype we developed with this novel technology. It's composed of 2 layers of elastomer gears in different shapes. Between them are jamming layers made of 7 layers of Meller films. When the air is vacuumed out, the prototype bent up and lead to an increased curvature. When adding a load of 60 grams on it, we can see that it's only slightly deformed. In contrast, as shown in the left figures, if there are no jamming layers, a same load will cause it to collapse and flat to flat and fall flat. It indicated that this technology also permits the increase of strength when vacuuming the air out. Meanwhile, as the jamming layers are inserted into the gap between between the 2 elastomer layers, so it do not increase any extra thickness. There is a figure presenting the principle of our prototypes. The main part is 2 layers of elastomer gears. They are designed to have uncompatible shapes, which means that they have different angles and different heights. A few layers of origami jamming sheets are sandwiched between them. They are laser cut to fit the shape of the larger elastomer gears. Their shape ensures they can be folded and inserted into the gap between the 2 elastomer layers. Around this sandwich structure, there is an airtight envelope in TPU film. When the air inside the structure is vacuumed out, the pressure gradient because of the atmosphere forces the 2 elastomer structures to come closer to each other. This will lead to the whole structure's bending and the curvature increasing, as the origami jamming sheets are cut to adapt the shape of elastomer gears. They will also bend together when the air is vacuumed out. When the whole structure is already bent, further vacuuming the air out will press the jamming sheet jammed together and leading to increased strength. To measure the curvature change of our prototypes, I fit a circle to its top surface. We can thus get its respective radius and curvature. To measure the strength of our prototype, we conducted a compression test for each prototype, as shown in the video. With the compression test, we can get the force displacement curve, then calculating the strength using the slope of this curve. With the curvature measurements, we found that compared with the prototype without jamming layer, our technology of inserting a jamming layer inside can slightly improve its curvature change. With jamming layer is measured to have a 12% larger curvature, and it's also measured to enhance the strength by 150%. This figure presents all our design parameters with this technology. You can find in detail in my thesis our study of their impact of the whole structure's curvature and strength. In summary, we developed a new technology to control UI's shape and strength using only one actuator, not increasing the UI thickness. This can help to address the stability-strength trade-off of soft materials like elastomers. With the technological explorations, we now have a lower technological barrier to use programmable soft material for constructing shape-changing UIs. It's also possible to enhance the strength of shape-changing UIs in soft materials, which can further broaden their application in human-computer interaction. However, the adoption of the new materials for constructing UIs introduces new factors that need to be considered when studying users' interaction experiments. So, let's go together to a new part of our user perception study. In this part, I conducted a psychophysical experiment to study the impact of a new factor, the thickness, which is introduced by using programmable soft materials. More specifically, I studied the impact of the softness on users' shape perception ability, currently focused on curvature perception. The perception of curvature of soft surfaces come into play with novel interaction. In HCI, different soft curved UIs have been explored, including daily soft curved object, UIs with customized softness and curvature, and curvature changing UIs. To ensure the efficiency of haptic feedback of soft curved UIs, user perception is now a bottleneck. HCI designers need to know user ability to perceive the curvature of a soft UI. In order to know user ability to perceive the curvature of a soft UI, we address 2 research questions. The first question is, how well can users perceive the curvature of a soft object? And the second question is, does the softness impact the perception of the curvature? To address these research questions, we conducted an experiment to study users' curvature perception, precision, and accuracy in different softness conditions. Our independent variables include 4 different levels of softnesses and 3 different levels of curvatures. I present here the 4 levels of softnesses that we studied. Below each is a daily object having similar softness. The first was designed to be softer than our index finger pads, which is similar to a gummy candy. The second level was designed to be as soft as our index finger pad, which is similar to a shoe heel insole. The third is harder than our index finger pad, which is similar to a rubber band. The last level is rigid, which is similar to a shoe heel. Okay, Here is a 3D model of a stimulus. Participants touch and explore top surface. The top surface has a different radius of curvature to investigate user perceptual sensitivity over a broad range of UI curvatures. We use 3 different curvatures as references, from very curved to little curved, like US used in previous research. For each curvature reference, participants were presented with 6 comparison stimuli, whose curvatures were around this reference. Our experiment used a standard 2 alternative forced choice procedure. That is, in each trial, we present participants with 1 reference stimulus and 1 random comparison stimulus from respective group. Participants touched and explored each stimulus successfully. Then, the participant had to indicate which of the 2 presented stimuli felt more curved. Here's a figure presenting a participant touching and exploring 1 stimulus in the experiment. During the experiment, the experimenter presented the first stimulus to her and told her to start the exploration. She touched and explored the first stimulus and then signaled to the experimenter that she completed the exploration. Then the experimenter switched the stimuli and asked her to explore the second one. Once she's done exploring the second one, she answered which one is curvier. With participants' answers, we can calculate the probability density of the answer. Then we can estimate the precision of their curvature perception and accuracy in different curvature and softness conditions. We measure the precision through the just noticeable difference, shortened as GND, and the accuracy through the point of subjective equality, shortened as PSE. I will now present some major findings of our experiment, starting with precision. Here's the result about participant curvature perception precision. The smaller GND means better precision. It's presented in this figure as x-axis in the unit of millimeters. We found that in the most curved condition, participants perceive with similar precision in all 4 surface conditions. In middle curved condition, participants perceive with similar precision in the 2 softest conditions. Participants also perceive with similar precision in the 2 hardest conditions. Comparing them, we found that participants perceive with better precision in the 2 hardest conditions than in the 2 softest conditions. In the flattest condition, participants generally perceive with better precision in the harder conditions. We also found that in each softest conditions, as the stimuli become flatter, participant GND increased, which means the precision increased or decreased. Here is the result of parallel fit of GND in different softness conditions. Point in this plot are data that we measured. We slightly jittered the data point to horizontally to avoid overlap. The curves are the fitted result. The exponent of the fitting result indicate how rapidly participant GND increase as the surface becomes flat. Larger exponents indicate a more rapid increase of GND. We can see that the exponent decreases from 1.76 to 1.45 as the stimuli become less soft. That is from short L010 to rigid. In addition, all exponents are larger than 1. This suggests that with a softer material, the difference in precision under different softness conditions may be larger as the surface becomes flat. Now, let's see together participants' perception accuracy. Here is the result of participants' perception accuracy in different curvature and softness conditions. It is presented in this figure as the x-axis in the unit of millimeters. We found that in each curvature condition, participants had similar accuracy in each softness conditions. We also found that participants tended to be less accurate when exploring less curved surfaces. Based on our experiment results, we provide some guidelines for future design of curvature and softness changing UIs. First, when curvature precision is crucial and it's not possible to use very curved UIs. For instance, on a large-scale soft display, such as this one, the curvature is used as a relative display of the curvature of a planet. Here, the Earth. Users should be able to precisely perceive rather large curvature radius. In this case, designers should focus on or change the stiffness to a more rigid material, for example, around sharp A30. When designers need to build UIs with a larger range of curvatures, for example, for toolkits such as this one, enabling a wide range of curvature for soft shape changing interfaces. In this case, designers should also focus on or changing the stiffness to more rigid material. Another guideline And for building precise soft curve UIs is to focus on very curved UIs, that is, radius around 10 millimeters. Where any softness can provide users with precise haptic curvature information. Similar to precision, designers should also focus on building very curved UI when accuracy is important, as they can also provide users with accurate haptic curvature information with any softness. For example, users can perceive as free if the number of messages received increased when they are in the meeting. Through the curvature of a soft watch capable of morphing into a very curved shape to timely notify precisely and accurately through the curvature. Based on the previous technology exploration and the user perception study, we can now go to the new part of new device design. In this part, I designed a novel wearable device using programmable software materials to provide users with novel haptic feedback. More specifically, it's a soft smartwatch with its back capable of changing its curvature to provide users with notifications. Smartwatches have become one of the most popular devices that we wear with us in our daily life. One of the most commonly used functions of a smartwatch is to receive notifications, for example, to be notified of a call, alarms, health alerts, and task reminders. Recently, shape-changing feedback has attracted the interest of HCI researchers. However, the technology they propose have disadvantages. For example, the design of a silicone membrane under a watch actuated by a piezoelectric actuator. However, it can create shape changes with very limited amplitude of a few millimeters, which limits the feedback possibility. In addition, piezoelectric actuation requires a high voltage. This may limit its application for devices worn on the body, although they limit the current. The design of wearing several inflatable silicon air chambers around the arm. However, this technology can only create isotropic deformation. It means that the silicon chamber is inflated in the same way everywhere, like a balloon, and therefore can create only a spherical shape. With our previous user perception study, we know that the ability to create highly curved surface is important to improve the shape perception of soft surfaces. It's therefore important to explore a wide range of creatures for soft surfaces when on the body. With my previous technological exploration of the new programmable software material, Bâtiment, it's possible to overcome the disadvantages of existing technology with their high shape-changing ability. Furthermore, the thickness is a critical factor when building wearable devices. To build a wearable shape-changing watch, I explored this technology and overcame related fabrication challenges to fabricate the thinnest Bâtiment. For example, one challenge was eliminating the bubble or applied in the silicone before drying, because the slightest imperfection has major consequence on the deformation of such a small prototype. You can find in detail in my thesis the techniques that we have found to fabricate very thin prototypes. After solving these fabrication challenges, we succeeded in fabricating very thin surfaces with a thickness of around 3 millimeters. We place these surfaces on the back of a watch to change its shape and provide users with haptic feedback. Compared with another technology providing haptic feedback through shape changes, our technology has several advantages. For example, the surface is thinner, the amplitude of the deformation is larger, creating anisotropic deformation, for example, from a flat shape to a cone shape. With this prototype, the first question we needed to answer was, which shape change makes the deformation more noticeable? To answer this question, we have developed two surfaces with different shape changes. One changed from flat to round, and the other changed flat to a more pointy shape. With the two surfaces we made, we conducted an experiment to measure the absolute detection threshold of shape change with 12 participants. Here is the setup of our experiment. Participant had the hand wearing the watch in a box and one headphone playing Brownian noise to avoid the impact from the noise of palms. During the experiment, participants tapped Y or N on the keyboard to indicate whether they felt a stimulus on their wrist. The independent variable of our experiment is the final shape of our surfaces, round or pointy. We measured the absolute detection threshold following a 2-down, 1-up staircase procedure. I present our staircase procedure with an example of a measurement of the threshold of our participant 9 with the pointy prototype. When she didn't feel the prototype stimulus, as indicated by the red dot, we increased its pressure inside the surface. When she felt the stimulus twice in a row with the same pressure, as indicated by the green dot, we reduced the pressure in the surfaces. After a few trials, the pressure at which she can feel the stimulus began to converge around 8 to 9 psi. We calculated the detection threshold with the average of the least 5 pressure values. In our experiment, for each participant, we measured the threshold 3 times for each surface. I present to you now the threshold that we measured with both surfaces. We found that participant threshold for both surfaces are rather low. We found the average threshold for detecting the feedback of a round surface is 3.5 psi and 4.2 psi for a pointing surface. With the threshold so low, we know that our technology can provide users with efficient haptic feedback. With pressure on their threshold, the two surfaces change their shape very little. With both thresholds so small, we find their differences are small. We found that their bootstrapped 95% confidence interval are largely overlapped. As the minimum threshold is very low, deformation is limited, and as a result, the major thresholds are close together. While our participants told us during the interview that they feel the difference in shape changes between the two surfaces. I will present to you some qualitative feedback that we collected during the interview. One term that emerged was enjoyment. 5 participants explicitly mentioned that the sensation was pleasant, for example. They said that it was very smooth, delicate, and there is a great deal of emotion involved. You can find in details in my thesis all the qualitative feedback that we collected during the experiment. In summary, we created thin and soft surfaces to provide users with novel haptic feedback. With the experiment, we know that these surfaces can provide users with efficient haptic feedback, and the qualitative result shows that our participants found the novel feedback enjoyable. Now, let's move to the last part of my presentation, conclusion and future work. I will start by my contributions. Emerging programmable surface materials provide a high potential to construct shape-changing UIs with their remarkable shape-changing ability. Meanwhile, some great challenges must be addressed. In this thesis, I focus on addressing challenges from these 3 aspects. As for technological challenges, I conducted technological exploration to using programmable surface materials to control different shape-changing UIs. With softmorphics, a series of soft shape-changing modules and the respective technical evaluations, it can significantly lower the technological barrier for other HCI researchers when constructing their UIs. We also developed a new technology to address the stretchability-strength trade-off of current programmable soft material. With jamming origami endoscoping, a new technology to control UI strength and shapes, it can help to broaden the application of soft materials in human-computer interaction. As for user behavior challenge, I conducted a psychophysical experiment to study the impact of softness, a new factor introduced by programmable soft materials, on users' shape perception ability. With this experiment, I found that very curved UI can provide users with precise and accurate shape information, even if they are made of very soft materials. Based on our experiment results, we also provide users with guidelines on constructing curvature changing UIs in soft materials. This experiment has already opened a new research avenue. For example, Gauche has recently extended our experiment from convex surfaces to concave surfaces. Lastly, based on our technological exploration and user perception study, I also designed a new device, that is, a soft smartwatch capable of changing the curvature to provide users with notifications. As thickness is a critical factor in wearable devices, we overcame several fabrication challenges to control very thin shape-changing UIs with a thickness of only 3 mm. With our experiment to measure user absolute detection threshold with the new device, we found that it can provide users with very efficient haptic feedback. That is, the detection threshold is very low. With the quantitative data that we collected, we also found that our participants enjoy this new feedback. Moreover, to ensure the integrity of our results, all components that I conducted during my thesis were registered before collecting the data. I have also made public all materials needed for our experiment replication. Here are some short-term future work. To address technological challenge, based on our technological exploration of programmable software materials, future work should continue to develop design tools for constructing a toolkit to realize various shape changes. This toolkit should also include our new technology of jamming origami and supernoodle to further improve this new technology of controlling US strengths and shape. I can combine it with other technologies to create more complex shapes and control their strengths. For example, a technology that 3D print plastic tiles on pre-stressed membrane. When released, the membrane shrinkage will cause these tiles to come closer to each other, thus causing a shape change. This permits to create some complex shape changes, for example, from flat shape to a Bâtiment mask. However, this technology can only create an irreversible shape change and does not control the strength. Future work can combine our technology with technologies like this to refine the shapes of our elastomer gears to create more complex shape changes. Facing user behavior challenge, previous work has studied with simulated videos how users would interpret different shape designs and what application areas they could imagine for each. Meanwhile, user experience can be different when watching a video or interacting with the physical UI. For example, Kim and her colleagues found that user preferred shape changing speed differs on video or a physical UI. We can thus extend the previous user study like this with soft morphisms, allowing users to watch, touch, and interact with different tangible shape changing UIs. Based on our user perception study of a solid convex curved shape, it's possible to extend our experiment to study user perception ability to more shapes. As for design challenges, based on the new device that I designed, we are currently conducting another experiment with it to measure users' more ecological detection threshold when they focus on another task. For example, when they are working or doing a more connectivity demanding tasks. Here are some long-term perspectives of research related to my thesis. One research orientation is to combine shape-changing UIs with mixed reality to provide users with a more immersive haptic feedback. With technological advances, it's already possible to provide other users highly advanced visual and audio display, smell rendering, and test rendering. Haptic feedback from touching physical objects is needed to improve further and enhance the realism of a virtual environment. Current technology rendering haptic feedback solves problems such as limited resolution and low portability. On the other hand, by combining other interaction modalities such as visual effect, user perception of shape can be different. For example, Tingy and his colleagues found that when touching a static curved object, while seeing a different shape overlaid on it in virtual environments, users can tolerate around 70% of creature differences. Similar experiments also measure user tolerance of haptic visual incoherence with other shape features such as softness and size. The emerging shape-changing UIs in programmable software materials bring new opportunities to address these challenges. Future work should be conducted to use them to improve haptic feedback in mixed reality. More specifically, as for resolution, my shape-changing modules have a high spatial resolution as they use software materials. However, each of them currently create only one type of shape-changing. Future work should consider combining different modules to create one UI that is capable of creating multiple shape changes. As for portability, our technology is already much more portable than previous work. Future work can continue in actuator and US miniaturization to further improve its portability. As for haptic study, I've currently studied user perception of creature. Future work can be extended to study other different shapes. It's also important to study users' perception of different shapes, both static and dynamic, by combining other interaction modality, such as with a visual effect overlay on them. By realizing all of this research, shape-changing UI should provide users with much better immersive haptic feedback to simulate different shapes that we might contact with our body in reality or in a virtual environment. This is my presentation. Thanks for your attention. Thank you. But this one do not work well. Or in fact, this one is not work. Do not work.
Oh, okay.
I think I can just move my computer face to you.
Just for open.
Yeah.
Okay, so thank you for your presentation. We will now start the discussion session.
Yeah.
And we will start with the two referees. And as we discussed before, I would like to give the floor to first Anne ROUDAUT and then Jan. This is okay for you. So Anne, if you have comments or questions for Zhuzhi.
Can you hear me well?
Yes. Very clear.
Well, first of all, I wanted to say thank you very much for the presentation. I thought it was very clear. And I think you broke the record of number of slides because I think they are under-indicated. I've never seen that many slides ever. But I think it's good way because you used a lot of animation and every time it was very following your flow in the way you were talking. So I think it was very good. I want to say as well, maybe first a comment about the thesis. Overall, I think this is very impressive. You've done a lot of work, and we've seen in your presentation that you've also published or you're in the process of publishing those. I think you've got an award at the EHM as well, or am I wrong? I think.
Yeah, I got the paper in this year, EHM.
Yeah, so congrats for that. I think what I really like as well with your thesis is that you're kind of closing the loop, right? Because you're looking at very perceptual aspects. Then you look into, okay, we understand a bit more human. You go into how do we build those things? And then you close the loop with, okay, let's try with an application example. So I think it was a very nice story altogether. I think I've told you already, I think that the middle chapter where you created this fantastic soft end skeleton I guess material is very exciting to me. I don't think I've said that too, but I think the word that struck me in the presentation was bio-inspired, because I guess if you think about animal, and you showed us at the beginning some octopus, and if you look about the animal kingdom, we have soft tissues and skeleton, and I think this was very clever to use these two in combination. So this is really great work.
Yes.
So now I have a few questions, and I guess they're a bit meta question, and you touch a little bit on your conclusion. So the first question I have, I guess, is talking about all the factors. And if you look about Morpheus, Morpheus Plus, obviously there is a lot of, there is possibly millions of factors, curvature and strength, and even if you touch it with one finger or the entire hand, or if it's on your body. So and you mentioned as well, potentially as well, depending on the context and the application. So there is a million things, potentially more factors that we could potentially use, as application and or to understand more about human. But obviously testing it with user studies one by one is very tricky. So do you have any thoughts about how we should do as a community to explore in a maybe efficient ways all these factors?
Yeah, in fact, in my thesis, I focus on creature, and for two main reasons. One is the creature is the most commonly used shape features in our research area. Many UIs are developed for changing creatures, and another thing is that the creature is one basic information that we use to encoding the different shapes. When we touch the surfaces, we can fill the different creature in different pods. Then we can go to global image for the shape of the whole shape. So if I will continue, I will focus on the creature, and I will list the creature as the most important one. Once the creature is thoroughly studied, I think it should help to study other creatures, other changing features too.
But how do you have an idea of, like, because I guess, you know, when you've done that study of curvature and softness, which softness I think actually doesn't even actually occur in Morphe, so maybe another factor. But like it took you, I guess, like a long time, right? You know, you need to do an experimental design and recruit participants, and you cannot test that much things, right? Because there is like the intrinsic limitation of doing a studies and getting some, I mean, I guess running some stats. How do you think we should go as a community? Should we test them one by one, or have you thought, maybe, I don't know, have you thought of any other way we can figure out more about that space, I guess, of factors?
Yeah, I think to do them one by one team or by one researcher is really challenging. But at the last workshop I participated, the workshop organized by Céline, we have talked about to create a community to share the different study of different technology to create different shape changing and UIs, and also to share our study of different study of user perception of different shape changing and feature. So for each specific applications, shape features, the shape feature which is the most important is different. Maybe someone is interested in size, someone is interested in strength, something like that. So it's interesting to form a community or work group to open source all studies, so we can know clearly what is done, what is not done.
Mm-hmm.
Yeah.
I think it would be really useful indeed to have some sort of repository of some sort, or yeah, if we can have people to collectively, you know, like, you know, rather than always searching for who's published, you know, a new study of the factors. So yeah, it would be a great idea, actually.
Yeah, and also there should be a cooperation between different areas. For example, our shape changing area, the haptic area, the physical area, and even the computer graphic area. So it should be a multidisciplinary community, and we share all our funding, all our needs, something like that.
Yeah, and I think it's also come to the fact that I mean, my feeling is that in the community, people are very so far tech based, right? You know, we have like an interesting material, and we're going to be testing that material, because there isn't much programmable material out there to test like this infinity of, like, you know, factors that there is. So so yeah, well, anyway, that was just me wondering. I guess this came down to my second question, which is about, you touched a little bit about it, about the toolkit, and the fact that in the community we don't have much technology to build those things. So we always tend to go from scratch, you know, like learning about silicon and learning about pneumatic and learning about actuation. And so I guess I have two questions related to that. I wanted to know first about your journey. I mean, I guess what's your background before, and how did you come across learning all about this different materials and actuation? And the second question is about how can we now make it more available for people to replicate?
Yeah. The first question, my background is that I started my bachelor and master also in mechanical engineering, and then I do a master in electronic engineering, and then I meet Céline. I started the HCI in computer science. So it's for my background is already multidisciplinary, so it can help me to address different challenges when we need to conduct experiment, to fabricate prototypes, something like that. And for the two questions, for the second questions, if we want to make our technology or different toolkit more accessible for other peoples, you should make all things open source. Like we are planning to publish instructable in the fabrication of our prototypes with all details. So for us and for others, if they can open source as much as possible, this can benefit all the community. Open source is always the always important and interesting.
Yeah, and I'm wondering if you can also develop a bit your ideas that you with the 3D printing at the end of your presentation. Like, can you tell us more about that idea? It's really interesting.
The toolkit.
Yes.
Yeah.
Which one was it? Sorry, I make you go through.
Yeah. This one.
Yes.
Yeah.
Yes.
Yeah, I can go to.
So how do you imagine, like, I guess, like, going for it? Like, what would you need to do?
In fact, the contribution, the most important contribution of this paper is the reverse problem in the area of computer graphic to study to simulate how we can use different shapes of tiles to create a more complex surface. So we can currently we develop only a cylindrical surface. It's simple. But if we can use their technology, their algorithm, their code to do the reverse problem for the shapes of our gears, so it should be possible to create a complex shape like them, because the principle is similar. It's the one, and there is a external stress. The tiles or the gears will become closer to each other, so create a global interface. So the technology is common, but we can we can try to combine with the algorithm to do the inverse problem.
So do you imagine this to be manually done then? Like you have those things that are 3D printed and those membrane, and you kind of assemble them?
Yes, I think once, because the fabrication for our prototypes and for theirs is not difficult. It's not difficult. It's just the most critical part is to decide which shape we need to print, or which shape of the gears we need to fabricate. So once we decide the shape, the fabrication should be easy.
I have a very weird question, I guess, because in my head I understand it differently. Do you think we can build a machine that automatize that? I mean, I guess it would be like, can you put like silicones or whatever kind of latex or any kind of other like soft material in some kind of dispenser system? I don't know. What your thoughts about that?
Yeah, for me, it's possible because for the HCI, we need also to consider the question of price. If we want to build a machine to do it, we need a pipeline to do different process. It should be very expensive, but technologically, I think it's possible.
Yeah.
Yeah.
Okay, cool. That got me excited.
Yeah, currently, we fabricate our prototype manually. We need to laser cut the germ layer. We should print the model of the elastomer structures, then fabricate the electrical structures, then assemble them. And for their technology of the button mask. They just 3D printed it. It's so for technological point of view, it's not possible to do it with machine, but to consider the price.
Yeah. Okay. Yeah. And then maybe the last question I have is that I maybe, I'm sorry if I forget, but I was trying to find it in the thesis, but I'm wondering then if you can talk a little bit about I mean, you're using a pump, right, in your studies, like to inflate and deflate.
Yeah.
How, I mean, I guess trying to push a little bit, like, in the future, I guess if you had a watch like that, how do you imagine the sort of actuation being integrated? Because I guess, like, minimum we can have like a small peristaltic motor maybe, but it's still quite big. So have you thought about, like, maybe if we want to push it to a consumer, what form would that take?
In fact, currently we haven't considered the portability of the motors. So we use the motors just buy in the market around 5 centimeters at length. But we built this prototype as we expect we need a high pressure to inflate the prototype. To maybe 12 psi, something like that. But with our experiment, we found that even 3 psi, 4 psi is already enough for user to fill the shift chain. So if we once we have conducted a more logical experiment, measurements of their threshold, if their threshold is still low, we can use very small pops. In the market, around 1 centimeter I've seen to provide around 4 psi as the pressure increase, something like that.
Yeah.
Yeah.
That's very interesting, and I guess it's nice to see it as well as, like, those investigation, those human factor investigation also help to refine the kind of, like, technology you need, right? You don't need like a really super competitive, like, actuator. Actually, you just need enough for the human to perceive. So
yeah,
that's very interesting.
Yeah.
Okay, that's it for me. I'll pass on to Jan, I guess.
Yes.
Thank you.
Great. Thank you, Anne. And thanks, Zhuzhi, for your presentation and letting me be part of this. This is really exciting stuff, and it's also closely linked to what we're doing. We saw some slides that you showed were referring back to our extended abstracts from last year. So I think we're very tightly linked in what we're trying to do here. So I have a few things that I wanted to comment on. So first of all, the best question that Anne just asked was, like, what's your background? And understanding that you come from an ME and an EE background and now are doing your PhD, that explains so much about what I saw in the thesis, because as a computer science background person, I was surprised to see the amount of just technical, measurement machinery thrown at every problem here in a good way, right? So I think that's one of the strengths of what you did. Like there are no questions left when it comes to, like, what's the exact technical performance, or what are the abilities of certain techniques that you had when it comes to, like, how far can we stretch this mechanically, and what's the capability of each mechanism that you proposed. So this is great. It also, I think, explains to a certain degree why, I guess, compared to what I'm used to seeing at CHI, I found that there's a little bit of a lack of push through on the software design tool side of things. I would have loved to see more about that, but in part that's because of my background, and that's in part also, I think, because CHI is often looking to see all the stuff that you now know about these things passed into a chunk of software thrown out there so other, smart grad students, smart and researchers can build on this. So you were mentioning that some of the things you're doing are actually heading towards a design tool. I think you brought this up in at least one of your chapters. Can you talk a little bit more about how far have you managed to move ahead on the side of casting the things that you've done into smart software design tools so other people can use results without having to become an expert in ME and EE and your specific, specialty now?
Yeah, good question. In fact, currently, due to the limits of the time of my PhD, I focus on the technological exploration to fabricate different ship changing prototypes. For me, well, me and Céline and Benoît, we haven't started yet to construct a real software for other HCI researchers to do it. But we have measured their shape changes, we have measured their strengths. So we have a database. We have database which allow us to create a software on it. For example, we can have an interface to users that we change the different parameters that we needed, and then we can search in the database which kind of strings it will create, which kind of shape change it will create. Then it will visualize the shape it will form, and to let the user to judge whether it's enough, and so she will refine the parameters to get the final design that she wants. And another thing that I want to combine, another two things I want to combine is one is the affinity analysis, is affinity element analysis. So it allows us to simulate different shape changes and different strength changes, and another to combine with the research question of inverse problem in computer graphic area. So combined with their technology, combined with our database that we measured, we should found a base to a database with all parameters, so all shape changes that we can make, and then let users to then create a software that below it to create the visualization etc. to facilitate users. Yeah.
Okay. I think this is definitely an avenue that would make a lot of sense. I mean, in part, I think this is maybe even more addressed at Céline really than what you're doing, because that needs to be something that continues, I think, in the lab, so to say. So you're aware of the different kinds of contributions that people make to HCI, right? Whether they're empirical contributions, artifacts, whole theories or models or something like this, or new research methods, or just a data set, for example. And so within like Jacob Roberg wrote this great breakdown of contribution types in HCI. And when it comes to artifact contributions, that's where the toolkits also fall, right? What do you think? Do you have a sense of what you would have to do to make a great toolkit? Like, what would be criteria for having a really good toolkit contribution in this space?
For us, if we made a toolkit for it, the most, as there is already many different toolkits already exist. For example, from your team, from the team of MIT Tangible Media Labs, for us, if we make a toolkit, the software development will not really be our contributions. Our contribution should still be the new technology, and the difficult for me while the difficulty to develop the toolkit is how to facilitate the users to choose what they want, because facing an interfaces, facing an interface, there are many factors that might change. Their curvature, their size, their strength, their frictions, like that. With our technology to fabrications, all the factors might change. So we need to find a way to facilitate users to better preview what it will get with this design.
Yeah, that's definitely a key challenge. And I mean, we're putting lots of effort into getting the simulation parts of our toolkits going, like, you know, with SoroCAD, trying to get simulation going and actually showing how shape change happens when you set certain parameters is already super tricky. So the kinds of things that you're varying are probably going to be even harder to get spot on simulations for. But I think that's definitely a key contribution there. So what I would recommend, this is really more a suggestion than a question. As you know, you've got soft morphes in the pipeline, right? About, you know, submitted or about to be submitted, and I would maybe be careful about using the word toolkit at the present stage. I think it is an enabling technology, maybe even a library. But when people hear toolkit, they tend to think that it's, you know, somewhat really ready-made software hardware combination. At least in the Kai community, I get that sense. You know, to let somebody who doesn't have the expertise build something with it and then explore the range of it. So in terms of expectation management for your reviewers and your readers of your papers, if you guys are you know, continuing that work, until there is a design software aspect to it, I would probably find some other label for it, because toolkit just puts you in a bag with lots of other people who have mostly focused on casting things into software as well.
Yeah, and so just and I prefer to call it like a technological exploration, and the toolkit is our future work to
talking about future work, I know you had your the shape changing watch exam, for example, was submitted to mobile HCI, and there were some other things where you said like it's in the works or being submitted or already submitted. Any updates since you compiled your you know, your PDF, so to say? Any updates on publication successes? Did we manage to maybe get another paper in or something accepted, or are you getting have you gotten initial feedback, reviews or something on anything else, or not yet? I mean, I don't know exactly what the deadlines are, so it's an open question, really.
Yeah, currently we have got one update is we got a minor revision for mobile HCI for the shape changing watch that we developed. In the thesis, I wrote that I published it in the French conference, and today it's already it's in minor revision for mobile HCI. So we are doing to publish it.
Nice. Yeah. So minor revision means you're basically in, right? You just need to change a couple of things. That's really good. Congratulations. One thing that I found a little confusing towards the beginning of the thesis was there was a section on like the value of curved objects, so to say, where you were talking about like what the value of having curved objects in general is. And that seemed a little less academically rigorous than the rest of your thesis, which is very much, you know, technical measurements and you know, give me data, right? So talk to me a little bit about like, why is that in there? Why is that in the thesis, and what was your process writing that up?
In fact, for me, or for us, the HCI researcher, the importance of creature is relatively evident. Because we see many creature changing UIs, and we have seen many study on creatures and like that. But when I wrote my thesis, I'm thinking about whether it's evident for all the people or not. So I try to add some examples around us, some daily objects. I let them know, you know, you're touching the curved objects every day. So how about we provide you a shape changing UI that can simulate the same, imitate the same shapes, can give you the similar perception, something like that. So I give some daily objects as examples. That was my initial motivation to do that.
Okay. Yeah, I think this. I mean, it's in the thesis now, and it's not breaking anything. But I would be careful if there are further write-ups for the papers or anything coming out of that. That is probably a section that doesn't seem to, be quite as academic as the rest of it, which is okay if you're motivating and drawing from real-world experience from the reader. That's okay, but in academic context, it seemed a little out of place.
Yeah, I think I will drop it down as a creature during my presentation to other people. I think I said I never find that I focus on creature is confusing. So I think I will drop out this section to make the contribution on my thesis to make my thesis more clear.
Yeah, I think there's actually something to be improved on that section for sure. Now, a couple more detailed questions on. Yeah, I do agree with Anne. I think the amount of slides that you had was a record. It's only beaten by the amount of references that you have in your PhD thesis. So on slide 284, you were talking about and you can usually enter the number and then just jump to it. You don't need to flip through everything.
Sorry, I did.
That's all right. Well, however you get there, it's not that far. 284.
84.
Yeah, 284.
This one.
Okay, so it was a close by. There was something about a study from somebody else that had done it with concave objects.
This one.
Yeah, that one. Okay, so I was off by one, I guess. What about it? I mean, this is interesting. Somebody else picked up your idea and extended your study to now concave objects. Did they confirm your results? What did you learn from what they found? Like, how does that change your results? Was it fitting in? Was it expanding them? Was it contradicting? Is there a new interesting question coming up? Can you talk about that a little?
In fact, I didn't read in detail for their experiment, because in my experiment, the major factor that I want to study is the impact of softness on creature. But they take inspiration from our experiment, from our experiment protocol, our public materials to reduce the experiment. But they study only the rigid surfaces, rigid concave surfaces, and rigid concave surfaces. So I do not really read in detail for their work, because it's not what really we are interested in.
Okay, so softness wasn't playing a role in their experiment. Okay, I see.
They redo our experiment and extend our experiment, but with rigid material only.
Okay. One other thing where you got some results that weren't. It looked like you weren't quite happy with the results yourself, right? When you had the dome pointing out from the watch, the round dome versus the sort of pointy expansion of it. You didn't quite get the differences that you were hoping for, I guess, right? In terms of detection.
Yeah, currently, because the threshold is really low, that's what we are not expected with such a low pressure. The two surfaces only slightly deformed. So we do not. Well, even with the camera, we take a picture, then we calculate the creature. The difference is not significant, not big. So we do not find really a big difference between the two. But during our experiment, it's interesting that visually we cannot find any difference. But during the experiment, our participants told us that they can find the difference.
Yeah, it's really exciting to see how good our sense of touch really is when it comes to these really light effects, right, on the surface. Is one of the things maybe that, I mean, you are inflating a rubbery object and you called it a pointy version, but I guess it wasn't really pointy, right? It was still essentially a curve, just of a much smaller radius than the other one. So would there be a way to get this so that it would actually be a much more pointy surface? Is there a way to do that technically?
I think with our technology, if we fine tuning the channel density, it's the density distribution who contribute to the global shape. If we finally tuning their density distribution, it might create some surface more curvy. But if we want to create some surface really curvy, you need to use a rigid material. You need to use because the surface material, when it's deformed, it creates always a continuous surface. So it's difficult to create a really pointy surface like with an angle or on the top. But if we have some rigid part on the top, it's the rigid part who contact with the users that might create some more pointy shape.
Okay. One thing that I thought was really cool was you registered your studies ahead of time, right? With the open science registration process. Kudos to that. So I like that. That was great. What I would like to understand, I mean, everybody should do this, right? I'm going to encourage my students to look more into this too. What I would like to understand from you, who has gone through the process, do you see any challenges doing this? Like, was there something that was particularly difficult about this whole doing this upfront registration? And do you see any disadvantages to it, to how you were able to conduct your research over the last couple of years? Like, was that process in any way problematic? I would like to understand.
Yeah, for me, currently I've already registered a fourth. I've conducted the fourth experiment, so we've registered fourth. We have done fourth registration. For me, it will not really give us a challenging to conduct our experiment. Instead, it can help to do our experiment, because when we do the registration, we need to think clearly what we plan to analyze, what data we plan to collect, and we write also the analysis script to do this. Once that is fixed, we can be more easier to conduct the experiment. Follow it. For me, it's not challenge, but it can help us to do it. But the first time I do it, it was with Céline. It's my first experiment to study the back of device interaction, something like that. Because in my first experiment, and it's beginning of my thesis, so we want to try some new things to see whether it goes well. And the first time we do not familiar with the procedures, so it costs a lot of time. But after that, it's for me, it's easy, and I'm familiar to do it. I'm aptitude to do it, and
okay.
I prefer to do it for if I will do other experiment, I prefer to do all experiment I will do, I think.
Yeah, because it helps you be clear about what you plan to actually do. Yeah, I see. Okay, interesting. Thank you. So this is more a terminology question, and I'm about to wrap up here. You talk about, at some point, you talk about organic user interfaces a lot in your text, but somehow that word doesn't make it into the title. It doesn't make it into the abstract. Did your position on that term change? Are you trying to like take it out of the thesis, but it's still in some parts of it, or was it introduced late? Like what's going on?
Yeah, in my thesis, I adopted the term of organic user interface. In fact, it's the same thing because organic interface is focused on two factors. One is soft, another is the curve. So I want to facilitate other audience, not from HCI researchers, to better understand what it is. So I use the organic user interface. But in fact, after discussing with Céline, and after reviewing your review and Anna's review, I found that maybe I can just go straight to the point. Shape change interfaces as my contribution as my structure, and to not relate it with organic user interfaces, because it's in my way to facilitate the other audience to understand it. But I found that it's not really difficult to understand. So I think it's also possible to drop off the idea of organic user interfaces to focus on shape changing interfaces.
Okay. So last one, the jamming stuff is really cool. I like what you did there. And you used it to change curvature and then sort of increase the rigidity of that curved object, right? Where else could you see this used? Like, can you tell me a little bit more about like what the potential for specifically this jamming could be for other kinds of shape change?
In fact, with the yeah. In fact, so as the example I demonstrated with the Bâtiment shape, is a good example. It's a good example as sorry, I will get it soon. Yeah,
that's okay.
Yeah. Yeah, you know here. In the end, he has a in the end of this video, it has emphasized it can create flat shape, saddle shape, and elliptical shape, something like that. So it means that if we combine our jamming and jamming origami and silicon with their technology, we can currently we create only the cylindrical surface with the positive Gaussian curvature. But if we combine with their technology, we can create the Gaussian curvature with 0, with the positive, with the negative. So once we can create different Gaussian surface with different Gaussian curvature, literally we can create most of the shapes that we want.
But isn't this kind of stuff what they're doing? Isn't that on a whole different level of resolution? This seems to be a fairly small scale pattern that they're using. Would you be able to do jamming on that sort of high level of detail, or is there a mechanical limit to how small the jamming technology can get?
Till now, the thinnest prototype that we do is around 4 millimeter or 5 millimeter. I cannot remember exactly, but the length is around 3 centimeters, something like that. So in this scale, I think it's possible, but you need to explore, because when the elastomer gears become too small, it might be tricky to insert the origami jamming layer inside. So this is the one I haven't explored. I think it's an interesting orientation to export to which scale that we can still insert the jamming origami layer inside and to still validate our technology. I think it's interesting to
Okay. Yeah, there could even be 2 resolutions, right? One could be the resolution of this overall shape change, and then maybe the rigidity could be something that happens at a lower scale of resolution. That's one thought that I had. Okay, so I guess last thing is I think 600 references. Boy, that's a lot. I mean, nothing against references, but the problem is the reason why you put a reference into a paper or a thesis is that you want the reader to know about some other work, right? And so usually whenever you put down a reference, you want to at least explain very briefly what's the point of that other work and what is their advantage, what is their disadvantage, what is the gap that they leave, what is the contribution that they make. And I don't think that's happening with all the 600 references that you have in your bibliography. So my suggestion for if you continue in the academic path is to, whenever you put something in and refer to another work, at least give the reader a very brief idea of what did they do, that particular work, you know, what is their contribution and what is the thing that is missing. If we just have these endless strings of numbers, you know, behind a, you know, shape change is an important topic, 15 references, for example, it doesn't really help the reader because they would have to go and look at each of these papers themselves. So you are doing part of a nice job for the reader if you actually detail out what each other paper told you and should tell the reader in, you know, just a half a sentence or so. But that's more a presentation question, nothing about the quality of the thesis. So yeah, I'm really happy. Thank you very much for letting us discuss this in a little bit more detail. And I'm happy to pass on the baton to the next person in the room.
Thank you.
So I guess it's my turn.
So now I will give the floor to the two examiners. So Kenny and Maud. So maybe Kenny, you would like to start first, and then
Sure.
Maud, will continue. Is that okay?
Sure, sure. Thank you very much, President. And first of all, yes, as the two reviewer mentioned, congratulations on all the efforts and results. It's very interesting and inspiring to listen to your presentation. Maybe my first question is a bit like a conceptual question. You cited the framework of OUI, Organic User Interface, in your thesis. I guess the first principle is input equals output. I'm just wondering, do you have any thoughts about integrating the inputs functionality or modality in your current prototypes? For example, now you can change shape, you can change many different parameters in terms of like size, length, heights. Do you have any thought about the shape can be also manipulated by the user, or like making it as a both sensing and actuating device?
Yes, yes, good question. In fact, as most of the technologies that I developed use the elastomer as a major materials, and we've already seen that in every community there are many sensors already developed based on elastomers. So, for example, we can add some liquid metals, or we can add some carbon particles inside the silicon on the silicon not dried. Then the elastomer can become conductive. Once the elastomer becomes conductive, it can be used as sensor, as touch, as a stretch, something like that, and as it's still elastomer, so it can still have a good suitability, and it's possible to partially replace the elastomers we use, or just insert them into our prototypes to validate the input function.
Do you think that sort of like the material sensibility will be affected or influenced when you change the shape? For example, it's stretched, then the conductivity maybe also change, making it less stable for a sensing device.
Yes, I think yes. We haven't explored it, but I think yes. And also, I think it's a trade-off, because for example, if we add some liquid metals, add some particle of carbon into the silicon to make it conductive, its suitability also become less than its original structure. So we need to explore whether whether our shape changing interface will impact their sensing ability, and also we need to study whether their sensing ability will harm the stretchability of our system, or the shape changing ability of our system. So I think it's a trade-off, and it should be explored.
Yes, thank you. Yeah, thank you for your comments on that. And also basically in all your prototypes, do you make it by yourself, like by hand, like using molding or whatever process?
Yeah, for
or is it a digitally fabricated process?
For all elastomer structures, we 3D printed their mold, then we molded it. And for the sophomorphism, so we molded the major part, then we molded the membrane, we stick them we glue them together, we fabricate the sophomorphism. And for the jamming origami and the silicone, it's 3 parts. For the elastomer part, we similarly we molded it with 3D printed mold, and we laser cut the jamming layers, and then we envelope, or then we do a membrane manually.
Yeah, I believe you have overcome several challenges, as you mentioned, like removing the bubbles and all those like side effects from those soft structures. Do you think this process can be carried out like in a digital fabrication process to reduce these kind of side effects or confounding factors? Like 3D prints, or like 3D prints silicon material or something like that?
In fact, Benoit, Benoit's lab, they are exploring that to 3D print directly the biomorph. I do not really know whether they can do it as small as the ones that we develop, but with current technology, that is the things that we can make. If we have a whole system for from 3D printing the mold and then vacuum out the silicon not drying to vacuum all the air bubbles and then pass to the another step to spray the membrane precisely and then use on and then glue them together. Yeah, it should be possible because the machine is always more precise than the human's hand. Yes, I think it's possible.
Yeah, I'm just thinking whether this would be massively produced. Yeah, as a like a mature product.
Yeah, for mass product, it's the same as answer as I have answered to Anne. I think it's a problem of price. Technologically, I think it's possible. And one challenge, one important challenge that I made in fabricating supermorphic is to we need to control precisely the because we have the major part of elastomer, we have the membrane of elastomer. We need to glue them together. The original solution is to glue them together with the silicone not drying, but it's really challenging to control precisely the thickness because if it's not thick enough, the structure is not strong enough. If it's too thick, it will fill all the channels, so it will not change. One possible thing that we can do to further improve it we can use plasma treatment, another physical technology, plasma treatment to glue all them together. It's easy. You do not need a layer of silicon, something like that. It's just a plasma treatment for the whole part, plasma treatment for the membrane. Then put them together. They will glue itself. I think with this we can further improve the thickness. Maybe we can do it with the machine.
Yeah, that'd be great if this could be like fabricated in a more easier way rather than like lab experiments by hand. So my next question will be about your perception experiments in terms of like you test JND and all those parameters. Just wondering, is there any similar research that has been carried out in the outside of HCI research, for example, psychophysical research area? They may use props, like prefabricated props of different curvatures, of different softness. Like imagine you have, maybe I can imagine maybe psychologists have done this already with already like prefabricated cubes there, and let the participants or subject to touch it and yeah. Do you know anything like that has been carried that has been done in the area outside of ACI, for example, psychology or whatever?
Yeah, in the haptic and the psychophysical research area, there are many experiments have already done. But we have also reference to this paper in the paper we published. But one thing is tricky that when we want to start to build our device, we want to know the impact of softness of creature, but we find nothing in their area. They studied the perception of creature, studied the perception of softness, but all the prototypes in different creatures is rigid, and all the prototype with different softness is flat. So we didn't find any results that can give us the idea what is the impact of softness on the perception of creature. So that's why we did it.
Okay, I'm just wondering if I don't use your prototype, which is actuated device, but I sort of like 3D print or even make by myself multiple objects there, multiple cubes there, and I carry out these experiments with the same protocol of yours, whether I can get a similar results or it will be a different results. Meaning your results is specifically for shape changing user interface.
In fact, for our experiment to of the impact softness of creature to limit the factors that might impact the experiment, we do not use shape changing US. We just molded the different structures in silicon. So it's not shape changing. It's just a silicon creature. So for your application, I think you can easily to use our protocol and to do similar experiments.
Okay, cool. That's cool. My last question is, so as you mentioned, as you show in one of the slides, there is a projection, like the Earth surface projected on the curved user interface, right? And you can see a lot of times in our real life, it's like this kind of curved user interface along with the visual feedbacks or other modalities of informations. And in your experiments, you mainly, I guess, you do it in a blind setting. So do you think your results can be applied to the situation or context when there is visual feedback or there's other types of maybe audio feedbacks? Would these kind of feedbacks or information affects the perception of curvature or softness?
Yes, I think I haven't done, but I think the real impact, because as the experiment done by I have presented this one. Yeah. Yeah, this one. We already know if we have the visual effect, even the shapes that we touch is not exactly as the visual effect. We can still think it's the same as the visual presentation. So the visual effect will of course will certainly impact our perception. But how to combine them? We should conduct experiments.
Just probably most of the time the visual sensation, visual modality is dominant. So I just wondering whether or not we need a high resolution for shape-changing user interface in terms of providing haptic feedbacks. Maybe a little bit just enough.
For example, in these examples, participants can tolerate around 60% of different change creature. I do not know what precisely, but from this work, I think combined with the visual effect, we do not need to change the surface as so precisely. We can change it a little bit, and it combined with the visual effect and give us a huge a change in our perception. Yeah, I think.
Cool. Thank you. Thank you very much. That's all my question. Thank you very much, and congratulations.
Thank you. There we are.
Thank you. So first of all, thanks for inviting me. So I'm very happy to be there today in presence, and then to be able also to test, because when we think about like changing interface, we'd like to test them, just to touch them. So it's I would be happy to test them afterwards, and and see and would be able to test this. I am very happy to be there. I was part of your CSI, so maybe like just to explain, there's like the committee during the PhD when you can discuss the research advancement of your work, and we did that by like just by video conference, and then I'm very happy to be there and to see all the improvements that you did since our last discussions, and at the end you managed to do like to do a very great work, like assembling all your contribution together, both in your manuscript and in your presentation. And it's a very nice presentation today that is very complimentary of what you did in your manuscript, and when you can explain all what you did, and we can see that in all your contribution, even if they can appear very different at the beginning, we see that there are like some common aspects, and you can link them together and see the history of your PhD. And given your background, we can understand how you built everything all together, and it's very interesting, and it's great work at the end. So congratulations for that. Especially like as it was mentioned, like you have like a strong knowledge of the literature, because you were able to manage to know and to be interested by the HCI part, which was not like your background, and then start to understand how we could put everything all together. And it was like very nice, especially also because you conducted like a user study and it was not your background, like it's like a more HCI background, and you were able to conduct this perception study in detail, and this is great. And then you mix this with the design and the implementation of devices. So at the end, it's really great. I should say that I liked very much your introduction of your presentation with Octopus. So you didn't know, but last year we presented at SIGGRAPH a physics-based model of suction cups, and we did simulation of Octopus. And I never thought that we could use Octopus as a HCI device at the end. And we did like simulation for other purpose, for robotic applications, but at the end, this is nice. So I was like, it was very funny at the beginning. Like, oh, we can use Octopus for other applications. So of course I have some questions remaining after all the other questions. I would like first to come back to the perception study. And as a haptic person, so when you have like this change of shape, this is a question of the threshold that you can have in the mechanoreceptor under your skin for feeling the shape. And we know that we don't have the same threshold for all our fingers. Yeah. And I think you did not test in your perception study all the fingers. And like in the perception study, but did you test like them like just like by hand and see if you have like some modification in your feeling with your different fingers?
For different fingers, I do not really know, but for literary review, we know that because if we explore the surface with the whole hand, it should be a larger surface, not as little as the one we use. If we have a larger surface, it's when we touch the surface, their change of curvature and also their change of length. Mm-hmm. So it can give us more information about their shape. So I think we should do it more precisely than the thresholds we have measured. Yeah.
Okay. Yeah. And yeah, because at the end, you have some recommendations that you provide at the end of this chapter and this paper about like the size and like saying that, for instance, when you should have like I think it's 1 centimeter with a 1 centimeter shape, you will have more accuracy in your sensations. And then we say, okay, this is for one finger. So as for one fingertip, yeah. And then could we apply the same for other part of the body and should be like the same results? And especially like linking to another contribution that you had, like the one with the watch. Yeah. And when you have like the watch, you put a size for your bumpy stuff. Yeah. And is it you found that we were like very sensitive to this difference of shape, even on the wrist part. And is this like the length of your bump was similar to the one of your fingertip in your perception study, or could we somehow link these results or see like a link between these two experiments?
No, in fact, it's we haven't linked these two experiments because in the experiment that was studied the impact of surface on curvature, but mm-hmm. not study the shape change interfaces it's molded silicon mold, so it does not change the shape, and it's solid. It's solid. And for the shape change for the shape changing watch, it's more than solid. It's a membrane of 3 millimeters, something like that. So it's changed. When we touch it or when we perceive it, it's not the same structure. So we cannot directly apply apply the result found in the first previous experiment in this one. But from the first one, we know that we can perceive very precisely, even the surface is soft. And we know that the finger is one of the most sensitive organs that we can use. So with what we expect is that in the wrist, maybe we have a worse sensitivity. So when you have a large threshold, but in fact we do not find that. We find even when the surface is slightly deformed with a curvature around maybe 20 millimeters, something like that, we already sense it. So I think it's the problem of shape changing interfaces vs no shape changing interfaces, because it can maybe during its changes shape, it can provide us other information that we can learn, we can observe. Comparing with touching a solid non-shape change stimuli. I think it's for this reason in the shape changing watch experiment we find attrition really low. Although it's not compare, we cannot compare it directly to the experiment we conducted, but it's much more low than our exception. Yeah.
Okay, so this is a good transition with this shape-changing interface with my next question. So with this, still with this watch and shape-changing on the watch, so compared to like the current watches that we have in our life, it's about like putting vibrations to have notifications.
Yeah.
So this is somehow like no shape changing. So you are not so it's still it's not the same mechanoreceptor under the skin, because you are sensitive to vibration, and while for the other you are sensitive to shape modification.
Yeah.
So this is not the same, exactly the same mechanism. Still we are using mechanoreceptor under our skin. So this is a little bit different. And we know like that for vibration, we have like a cognitive load limit. And under this cognitive load limit, when you put too many vibrations, at some point, you don't feel anything anymore. I mean, you are still like fed up with like vibrations.
Yeah.
And I was wondering if you have tested with this shape-changing stuff, the cognitive load of the user, like if like doing some like a certain number of shape-changing, and at some point, like your user like gave some feedback saying, okay, I am fed up with like shape changing, I cannot feel anything anymore, or you did not observe anything about that?
We haven't done that. Because when I present this project in Aachen, I already mentioned that it's really interesting to do a long-term study like that, because if we want to use it as a real application, it should do a long-term study to ask the participant to react for a long time.
Yeah.
It's we haven't done it, but it's a very interesting application to continue.
Yeah, I think so. Yeah, but this is promising, because I guess like for people that are very sensitive to vibrations, like using other mechanism or other stimuli could be helpful for some of them to get the notification when you don't want to have like a visual feedback.
Yeah.
Then still like for the jamming endoskeleton, so you did like a very nice device, and then we say, okay, so this is a very nice device. Have you tried to do any user study to evaluate the curvature modifications, or you did not perform anything for the moment?
We haven't done it. This project I haven't finished yet, because about we already planning. We already planning flight to do it, but we don't know when, because to use it, a user study is necessary to do it.
Yeah.
It may be a separated project. The first project focus on the device. We publish this, and we make all material public, so other people can develop the same device. And the second project is the user study and real applications. Yeah. Currently, it's a field that where we do not have the time to do it, but it's always interesting to continue to use the technology and do the user study and the real applications.
Yeah, especially when you are like designing so many devices you did during your PhDs, and it opened a lot of different questions, and you have like a lot of experiments that could be performed. But of course, we can understand that you don't have time to do everything.
Yeah.
But still, it comes with my next question. Like it was already like asked by like Kenin before about the visual feedback, because at some point we would like to say, okay, but we were not like only with haptic feedback. We have other sensory modalities, and we could combine them all together. And yeah, like you presented the study that we did with for VR, like with a virtual environment. But I was thinking, like, even for you have like the visual feedback is for real, like not in a virtual environment. Yeah. We still know that we could manage somehow to have like situations where we know that putting together touch plus visual feedback is better than just having only visual feedback alone. So well, for VR, we know that of course we can somehow cheat a little bit because we can't see the real object, but for even for the real environment, like for your jamming on the skeleton, have you seen like any sensations like do you see how you could somehow test this combination of like this visual haptic feedbacks that you could see?
We haven't done it, but we just fastly I cooperate it with another PhD student team. We just fastly test by ourselves to touch it blindly. We can feel the change of strength, but the combination of them, we do not have any idea. But as softness it impacts our perception of creature. As our technology allow to increase the strength, so I think it should improve our perception. And when we can see as a visual effect together, for the shape, be sure. For the shape, of course, we can get more treasure, but for the softness, I'm not sure because we did not do the study in the direction impact of creature in softness. But on the impact of something in creature, we know that I'm not sure. I'm sure that with the German algorithm we can have a better perception threshold. We can also combine with the visual effect. We can also better perception threshold for the creature. But softness, we don't know yet.
Okay. Yeah. It's another type of experiment that you could do in another PhD.
Yeah.
Okay. And my last question would be about like I guess I will use the word of soft morphy when you did like a different type of I would say criterion, like you try to explore different type of criterion and different properties at the end. And my question is, when we see the different one like separately, then at some point we say, okay, we would like to combine them. And then when you think about this, you need, okay, but I need to transition somehow between the different properties or see how we could combine them. Have you already any idea about like how we could combine them or how we could do the transition between them?
I think do the transition is relatively challenging because it's not like the two matrix of activity pins. You can just change the head of each pin, can create many shape change. But for the amorphous, each time can only do one. But if we want to combine different shapes, you need to different shapes of air channels, different air channels. Two solutions. One is to overlay them. We can develop multiple layers of biomorph. This need to 3D print the elastomers structure directly. For this one, maybe we can choose which layer to actuate to create the form. But of course, for example, if there are 3 layers of shapes, we activate this as the middle one. The one in top will in fact the shape of the middle one. So it will be challenging to transit between them. Another solution is to do not overlay them, but create a surface rather large with different shape patterns in different regions. And then, for example, in VR, we can have a device to once we need to change the shape, we can move the device contact with the user finger to another to do the transition like that. To transition directly through one UI is challenging because there are the problems I have mentioned.
Yeah. Okay. Yeah. Sounds interesting still, but challenging, but sounds interesting. Yeah. So thank you very much and congratulations again for your work.
Thank you.
Thank you. So now I will ask you one question, just quick question before giving the floor to the PhD supervisors to conclude this discussion. I have plenty of questions, but I have time to ask your question in the afternoon, tomorrow, whatever. So I just have one question. Coming back to what Jan was speaking about the terminology and toolkit, we discussed that yesterday night, So I do believe that being in the computer science part of HEI, toolkit for me means something else, for sure. So we discussed with Maud, we said maybe repository or whatever. But thinking about that, the knowledge you have that I don't have, being on the computer science part, is more about the design parameter of the technologies that you explore. And for example, if you come back to this nice contribution that you call jamming origami endoskeleton technology, do you remember what was your design process? What are the design parameters that you explore to finally end up with this nice contribution? Because that will be the knowledge that I don't know and I would like to learn.
Yeah, in fact, I can go quickly to the parameters that we want to study. Yeah. Yeah.
Because I believe you have a set of design parameters that you explore. You did not end up directly with your solution. So how did you succeed? How did you end up with this solution?
In fact, as the shape change principle mechanism of our technology is the incompatible shape between the two gears. So directly we have the parameters. For example, the different thickness between them.
Okay.
The different angles between them, because it decide whether their shapes are compatible or not. And we have the thickness of the thicker one because it will decide the thickness of the whole structure, and the thickness is important for HI applications, and also the thickness of membrane because we after the first test with after the first experiment test, we found that our product cannot go to exactly the shape we expected. For example, expected it can bend in more than 200 degrees, something like that, but it will only 80 degrees, something like that. We found that the membrane between the gears it will avoid the whole structure to continue to bend because it will boggling the membrane is boggling and avoid the whole structure to bend. So we study also the membrane thickness.
Okay, so it was very experimental, the approach. You try, you see, you say, oh my God, now I have this, and you come back and you modify the parameters.
Yeah.
That's the way you end up with the solution.
Yeah.
Oh, I see. Okay.
Yeah. And it's currently it's focused on technology exploration and technology design.
Right.
Further study we can focus on user size. For example, which parameter is important for user. For example, maybe the thickness is global, the length global, the width global. Maybe something like that is more important for users. Yeah.
But you don't have, for example, with all the design parameters here, you need to experiment. So you don't have a formula and you use a kind of any kind of simulation to see how it will be.
We do it, and in the thesis we provide it. We measure the impact of different parameters, and we measure the creature, we measure strength. We have do a linear regression. We have provide an equation with which we can it suggests us with this parameter it gives us this kind of shape change, this kind of strength. It exists.
Okay. Yeah.
Yeah.
So thank you. I will ask further question, but later we have time. So now to conclude the discussion, I will give the floor to the two PhD supervisors. And I think we will start. We said that I will first give the floor to Benoît and then Céline. So
That's
Benoît,
great.
you have the floor.
Thank you very much. Thank you, Zhuzhi, to have me part of this adventure. I'm officially co-advisor, but can you hear me? Yeah.
Yeah.
Yeah, I'm actually co-advisor, but really, I didn't contribute much to your work. I was kind of a consultant, but I think we discussed maybe 5 or 6 times during your PhD. So I got to observe the progress and learn about your trajectory. It was very impressive. You also came to Paris a couple of times and worked with a student here who was there. Tian, he's online, so he could also testify how you drove this work very independently. I was very impressed because I thought that the project would be to explore the potential in HCI of technology that we have been working on for several years, and we started to develop and understand. But so you not only you did this, but very quickly you wanted to do something more and learn about how and maybe design a new system that would be able to have some stiffness change. And this is something I really find very difficult. We were struggling. We were really dreaming of this also in the lab, but realizing that it was really like a physics question, like a difficult physics question. And you really came very quickly with very clever and very creative ideas. And maybe to answer also Laurent's question, there was many different attempts with very different strategy that you don't mention at all. And I think that they were still interesting, but Zhuzhi said, "Oh no, this will be too thick." So I think there was a lot of interesting physics that came, but you that you came up with, but you discarded because you really were focused on a very ambitious goal. So I witnessed that you developed, or you have a very broad expertise with this very technical thing of starting from scratch in Grenoble, building samples and coming in Paris sometimes to measure their performance. So engineering, physics, experimental techniques in fabrication, in addition to the design and also the user studies, which are completely out of my discipline. So congratulations for all these achievements. I was really impressed by your results and by the breadth of difference, but also the creativity and the number of new systems that you created. So thank you, Zhuzhi.
Céline, you have the last word.
Maybe you can put the mic. Okay, thanks. Okay, so I'm not going to ask questions because we had plenty of time to discuss all the work during the thesis. But I wanted to stress the impressive amount of work that you did during the thesis, also very efficiently. So that was a very strong strength of yours, and always like thinking in a very logical manner. So that was also very beneficial to the research. And I also want to comment on the fact that you were always very calm and confident when you worked during the thesis. That was also very cool to work with you. And although that you are known to everyone to work a lot and very like being a hard worker in the lab, I want also to stress that you are able to plan the work in a realistic way. So it's not that you take up tasks without thinking. So it's also what you can do, your limits also. So that was very nice to work with you for that reason also. I think the theory understood, but you also picked up HCI very quickly because you were not from this field. So you started from scratch, not knowing about the field. And you understood very quickly the field and what we need to achieve a contribution in that field. So that was also very impressive. I want also to stress one difficulty is that this was a multidisciplinary topic. And it's known to be difficult to handle.
because you need to understand both fields and be able to mount some contribution based on both fields. So that's really not easy. And you were even able, as Benoît said, to propose contributions, like new ideas that were really on the edge between the two fields. So that's also something that was very impressive. I wanted also to comment on your ability to aim for the best work possible. So trying to pay attention to a lot of details. So I think people saw that also in your contributions, that you really try to do something as perfect as you can. So that's also it makes very interesting contributions in the end. So I think all those qualities together will make you a very successful researcher in the remainder of this journey, in your career. And I was very happy to be there for the beginning of this journey as a researcher. So thank you and congrats.
Thank you. So before the jury will go to deliberate, I'd like to ask if there are other questions from the members of the jury that you really would like to ask Zhuzhi. We have time if you want, if you have more questions. Okay, there is question in the audience. Someone with a PhD, that's better, but no. Okay, so I think we'll go to deliberate in the other room and we'll come back and after deliberation. Okay. So we will go to another room and we will.
I will send you another link so that we are just the jury by email right now.
We're leaving this one, right? Are we leaving this this Zoom and joining?
So members of the jury, we can move to the other Zoom room. Thank you.
Okay, so I would like to report what the jury wanted to say about your defense and what they wanted to highlight. So first, we underlined the quality of your presentation that was well articulated, engaged with the audience, and we really appreciate the quality of the presentation, and also that it was well illustrated with videos, because you use the video to show shape changing. That was very useful to and be complement. It was very useful in comparison with the document. So it was a good complement to the document. So we highlight the quality of the presentation. We also wanted to say the jury would like to underline the multidisciplinarity and creativity and the successful multidisciplinarity of your work, which is really multidisciplinary is a key word in the academic world. We always say multidisciplinary, but it's extremely difficult, and we wanted to really underline the successful multidisciplinarity and creativity of your work. So that combine both material and we call it material engineering and HCL. So that's really something to be highlighted. And also the second main point that the jury was really impressed by the, I would say, the diversity of contributions that ranging from technological, experimental, and conceptual contributions. So that was something that we wanted to highlight. And the jury also really enjoys how you answer the question. And it was a set of questions were both about very details about your work and also about long-term implications and research directions. And the jury really considers that you give very good answer to the two different types of questions. So it was very good. And for all these reasons, without any hesitation, the jury congratulates you for your work and award you the degree of Doctor of University Grenoble Alpes. And in French, pour toutes ces raisons, le jury a décidé à l'unanimité de te décerner le grade de docteur de l'Université de Grenoble. Toutes mes félicitations.
le serment à faire, je sais pas si tu veux le donner ça.
Tu as le choix.
What is your
Do you want to do it or not?
There's the English version of the
So maybe in English, because else you want to be understand.
So in the presence of my peers, with the completion of my doctorate in computer science, in my quest for knowledge, I have carried out demanding research, demonstrated integral, rigor, ethical reflection, and respect for the principle of research integrity. As I pursue my professional career, whatever my chosen field, I pledge to, for the greatest of my ability, to continue to maintain the integrity of my relationship to knowledge in my method and in my results. Thank you all jury members to come here to give me those invaluable questions and to give me all the inspirations that I can continue for my research career. It's invaluable for me to continue it with your suggestions, with your advices, like that. And thank you my my advisor Benoît. Even I give you some once I demand you some question really stupid for some in point of our physics, you always answer me with details to tell me to advance. And thanks for Céline. I thought literally with no knowledge about HCI, and you guide me to do this with in different aspects from science aspect, technology aspect, and the emotional aspects. So thank you. Thanks for all my friends online and in presence to come for my defense. And thanks to my family to support my emotionally. They cannot come. And thanks, lastly, thanks to my fiancé Junkai. Without you, I don't know how I support this year's, particularly during the COVID. I don't know if I'm alone. I don't know how I can continue. Thanks a lot.